Now I come to example 2. This one is going to be a follow-up to the previous example of a container of gas, the same number of moles, 40, the same initial temperature, 300.84, the same initial volume, the same final volume, so 0.5 cubic meters, the final volume 1.5 cubic meters, the initial internal energy is 150 kilojoules, the initial pressure 2 times 10 to the 5th pascals. Then we have here a graph of pressure versus volume. So we have here the initial pressure, which is this, the initial volume, and then we are told that the volume is increasing according to this arbitrary equation, P is equal to alpha volume cubed, right? So we need to find what alpha is, and then after doing that, we can find out what the final pressure is here, P final, V final, we can find out the heat into the gas, and then the work done by the gas, and all of that other stuff. Then we can make a complete cycle out of that, right? So let's first find what alpha needs to be. This equation is given to you such that the pressure is expressed in atmospheres, not pascals. See here, the vertical axis is in atmospheres. So let's convert our initial pressure to atmospheres, and then later when we do our calculation, we'll convert back to pascals. So initial pressure, 2 times 10 to the 5th pascal. We can say 1.013 times 10 to the 5th pascal is 1 atmosphere, right? Then we can convert that. So then I can find out what alpha needs to be in order to satisfy that equation. So I can say 1.974 atmosphere is equal to alpha, and then the volume is 0.5 cubic meter, and then we're going to cube that, right? So alpha is going to be equal to what? Alpha is going to have the units of atmospheres divided by meter cube is going to be meter to the 9th. So it's such a unit that, so that when you work this out, the right side and the left side agree with their units, right? Alpha. So then we can put that in. Okay, so we have P is equal to 15.792 volume to the 3rd, right? So now I can put down 1.5 cubic meters here for the final volume, and then we can calculate the final pressure, right? The pressure goes way, way up, right? So in the graph, it would be way, way, way up here somewhere. 15.792 V cubed dV, and then from 0.5 to 1.5, right? Okay, so the work would be equal to the 4th over 4, then from 0.5 to 1.5, so 15.792 over 4, and then we're going to have here 1.5 to the power 4 minus 0.5 to the power 4. Remember that the pressure here was in atmosphere, so I have to convert that to pascals. The final answer will come out to be joules, right? So then we're going to say here, the answer was 1,999.6 kilojoules, but it's approximately 2,000 kilojoules, right? So the work done by the gas is basically the area under this graph. That's a very, very huge graph, 2,000 kilojoules, right? We can also find out the final temperature of the gas, and then the change in internal energy of the gas, right? And then the heat into the gas. Very hot, right? So we have here 53.298 times 1.013 times 10 to the power 5 times 1.5, 4,364.1 Kelvin. So the temperature really skyrockets, right? So of course this is not an exact problem that could happen, because something that hot would basically turn into a star, right? It would be very, very hot. So so then we can calculate the change in internal energy of the gas, right? Delta E is going to be equal to 3 halves nR delta T. So 3 halves 48.31, and then the delta T would be 24,364.1 minus 300.84, right? So then you subtract the initial temperature from that, okay? So then we can calculate how much heat is coming into the gas, right? So we say here, heat into gas equals to change in internal energy of gas plus the work done by gas, right? So the heat into the gas, we don't know. Change in the internal energy of the gas, 12,000 kilojoules, right? And then the work done by the gas, well, we found out that the gas did 2,000 kilojoules of work. 2,000 kilojoules of work. So that would be 14,000 kilojoules, or we can even write 14 megajoules. Right? So basically the result of this is that you're putting in 14 megajoules of energy into the gas. That's how much heat you're putting in. The gas is doing 2,000 kilojoules as a result of that. And then the change in internal energy of the gas is 12,000 kilojoules. So the temperature is shooting way high, right? So this gives you an example of a case where the equation is some arbitrary equation, and then you're going from a certain volume to another volume, and then you have some random equation, so you have to find the alpha first, then you have to integrate that, and then from there you can find the final conditions, and then from there you can use the first law of thermodynamics to find out what is the heat coming in, and then the work is already done by the integral, and then the change in the internal energy is done by changing finding the delta T and then multiplying by 3/2 nR delta T, right? Now what if we come back here isobarically, right? And then come back down isovolumically. So make it a whole process again, a complete process. So what would be the work done in the isobaric? In the coming back this way isobarically, that's equal to P delta V. So P times V final minus V initial. So what is the pressure of the gas? 53.298, but then change that to Pascal. Final volume 0.5 minus the initial volume 1.5. Okay, so let's see if that makes sense. Well, the area under this graph was 2,000 kilojoules, right? 2,000 kilojoules. So going back, you're going to do negative work, and the area is going to be the whole graph, right? So the whole thing. So, of course, then, if it's the whole thing, it's going to be larger, and it's going to be negative, so the answer makes sense, negative 5,400 kilojoules, right? How about the heat into the gas or out of the gas, right? Here we saw that in the initial stage, we saw that the heat was coming into the gas. Okay, how much heat was coming in? 14,000 kilojoules, which also equal 14 megajoules, right? And then what's happening here? So we can say here, Q into gas is equal to change in internal energy of gas plus work done by gas. We need to find out what the temperature there in that corner is. So what's the temperature there? PV is equal to nRT. So the easier way to do this, rather than putting the pressure, the volume, and the number of moles and the ideal gas law, is just to say PV, so that we can take the pressure here, or we can even take the pressure here, right? Either one. So we can say P initial, volume initial, divided by T initial is equal to the pressure up there, right? We can give this any label, P prime, V prime over T prime, right? So I want to find the temperature over here, right? So I can say the initial pressure is 2 times 10 to the 5th Pascal. The initial volume is 0.5 cubic meter. The initial temperature was 300.84. Okay, the pressure up here is equal to Pascal, right? The volume is going to be what? Well, the volume here and the volume here are both the same, so we can say 0.5 over the temperature over here, right? So actually, I don't even need the volume, V prime and V initial. Since these two are the same volume, then I can get rid of that, 0.5, 0.5, and then just worry about the temperature. So the T prime is going to be 53.298 times 1.013 times 10 to the 5th times the temperature initial divided by this, okay? So then I can find out the change in internal energy, right? And then from there I can find out the heat into the gas. So what's the change in internal energy? Delta E is going to be over here. It's going to be 3/2 times 40 times 8.31. The delta E of the gas is going to be negative 8,099 kilojoules in going from here to here. And then the heat into the gas Q into gas is going to equal negative 8,099. And then the work by the gas was negative, it was 5,400. So the gas is doing negative work and the heat is escaping the gas, right? So the heat is escaping. And then here heat is coming in, right? And then we can say that Q into gas is equal to, is the heat escaping the system, right? So here, 13,499 kilojoules escape the system, right? Here, 14,000 kilojoules came into the system, right? And then we can do the last step now, right? Times 8.31, and then the T final is 300.84 minus the T initial. Well, the temperature that it begins here is 8,121, right? 8,121.3 drops from here to here, and then it drops one more time, right? From here to here, okay? So then the heat into gas is equal to delta E plus the work done by the gas. But then on the last stage, it doesn't do any work, right? So the work done by the gas is 0, and the delta E is going to be negative 3899. So then the heat is also escaping the gas, negative 3,899 kilojoules. Okay? So this will be the final picture. 14,000 kilojoules coming in, 13,499 kilojoules going out, and negative 3,899 kilojoules going out in this last step, right? Now we can apply the first law of thermodynamics to the whole process and see if the total answer makes sense, right? So we can say the heat into gas total is equal to the work done by the gas total plus the change in internal energy of the gas total. Right? The change in internal energy of the gas total is 0. The heat into the gas, well, here 14,000 kilojoules came in. Here 13,499 kilojoules went out. Here 3,899 kilojoules went out. What was the work done by the gas? The work done by the gas in going from here to here was 2,000 kilojoules, right? And then the work done by the gas in going from here to here, we said was 5,400 kilojoules, right? 5,400 kilojoules. So if we add all of that up, so we're going to have here 14,000 minus 13,499 minus 3,899. 400 negative 3,400 kilojoules. That's a big happy face right there, right? So you have made a complete circle and you have accumulated all the heats and you have accounted for all of the work done, right? And then the total change in internal energy of the gas for the whole process is 0, okay? So you can see a couple good examples here of general processes combined with making a whole cycle with an isobaric or isovolumic or isothermal process, right? Thank you very much.